Okay, so as we mentioned before, the application of the Bernoulli, usually we wondering to compute how the flow velocity in our pipe. So this is a very good exercise. As you can see, this is a nano. Okay, we have a nano here, and we have two different cross sections. The first cross section is here, and the second cross section is here. So we may pick out the one point here. We call that the P point 1, and we pick out another point in here is a point 2. And for this case, we should check maybe along the center line is our string line. So this is our string line. So we have the string line, and the 2 points I pick up are located at the same string line. And you can see there is a different diffraction height. Here we have a diffraction height 1 meters, and the second is a diffraction height is 0.5 meters. So what's the purpose for this exercise? We wondering to answer the velocity in the stored sections. So the idea is we didn't know the velocity for the V2. So we need to answer the V2 in here. So we need to answer the V2 in here. And there is the V1 velocity. Okay? And you can see there are some sentences. We know that the velocity in the throw section is twice as larger as the approach sections. So this sentence, we know that the condition is the V2 is 2 times of the V1. Okay, so we have all the condition here. So can we compute the velocity V2? Yes, we can. So first we apply the Bernoulli equations. So we have the Bernoulli equations, and then we actually know the P1 plus the gamma Z1 and plus the 2 and the low V1 square will equal to the P2 plus the gamma Z2 and plus the 2 over low V2 square over 2. Okay, so as you can see, we need to know the piezometric pressure difference, and then the flow will start to flow in. So right now we only have a diffraction height, so we rewrite the pressure form to be the header form. So we know that the P1, the gamma plus the Z1, and there is our piezometric head. So I call that is the head 1. So this is the piezometric head, and I use the Z1. Okay, and later we plus again is equal to the 2G V1 square. Will equal to, again, we have the P2 divided the gamma and plus the Z2. And this is our piezometric head for the section 2. So and I call that is the piezometric head HD2 and plus the 2G V2 squared. Okay? Why I use the piezometric head? Because for our exercise, we only have the information about the piezometric head height. Okay, so we know that we rewrite the equation is equal to the piezometric head 1 minus the piezometric head 2 will equal to the 2G1, and the inside is the V2 squared minus the V1 squared. Okay, and we know that the V1 2 times is equal to the V2. So we can rewrite here, and we keep the V2 square, and we replace the V1 by the V2. And we know that the V1 is equal to 0.V2 and square. Okay. So we can just rearrange the equations. So we know that the V2 square minus the 0.5 square V2 square will equal to the 2G, and the inside is the piezometric head difference. Okay, so you can put, maybe I can become simple. So we have the V2 square, and there is a 1 minus the 0.25. Okay, and will equal to the 2 times the gravity is 9.81, and here is a meter per second square, and the piezometric head difference is the 1 meter minus the 0.5 meter. Okay, so you can compute the answer. So the 2 multiply 9.81 multiply 0.5 and divided 0.75. So that's equal to the 13.08 meter square in a second square. So you will take a root of the number. It's equal to the 3.6 around the 2 and the meter per second. Okay, so that's a very simple exercise. We apply the Bernoulli equations, and we will know how the difference, how the velocity difference they are, and we know that we can compute the velocity at any point we want, just based on the Bernoulli equations. And when you apply the Bernoulli equation, you should consider any 2 points you pick up, they are located at the same straight line. If the different points located at a different straight line, you cannot satisfy the Bernoulli equations. Okay? So that's one of the very famous application for the decatings. As me, I really like to drink the wine, so sometimes the testing of the wine is very important for me. So that's a very famous idea. When we have the decating, what are the meanings? So sometimes for the older red wine, there will have some sediments deposit on the bottle of the wine, and most of the deposit sediments, we call that the tannin. Okay, we call that the tannin. And the tannin will affect the tasting of the red wine. You will don't like the red wine with the tannin. So that's a decatur. This is the decatur. Okay, we have the decatur. And the idea is if the tannin mix with the air, the tannin will be softened, 软化, and then the sediment can be disappear, and your tasting of the red wine will be improved. Okay, so the idea is, can we speed up the mixing the wine with the air? If we can, and we can do the decanting very quickly. So that's the ideas. We design the decanters here, and you can see there is a small hole. And as we understand, we have a small hole, And that indicates the velocity in here will increase, right? And based on the Bernoulli equations, when the velocity increase, the pressure should be decreased. So the idea is there is, as I use the yellow color regions, there is the lower pressure regions. And the outside, the environment here, the outside environment here is the high pressures. So as we know, the higher pressure will flow inside to the lower pressure regions. So that's why the decatur, there is a small hole in there and will have the highest velocity result the lower pressure environment. And the environment atmosphere are high pressure regions. So the higher pressure region air will flow inside the lower pressure region very quickly. So that will speed up the decaying behaviors. So that's why we call that the decatur 醒酒器. That will just mix the wine with the air quickly. Okay, that's the idea. So that's a very simple idea. If we apply the Bernoulli equation, we certainly know the high speed result the small pressure. The high speed result the small pressure. Okay, so let the table quickly summarize the Bernoulli equation with the head form and with the pressure form. And there are some recommendations if you apply the different case study. That's for example, the textbook suggests you use the header form for the liquid and use the pressure form for the gas. But I guess it's no difference, just depend on you, belong to your questions, what the parameter you have. But most important thing, when you apply the Bernoulli equation, you should keep in mind the 2 points you want are located at the same straight line. And the second flow is steady flow, inviscid flow, and incompressible flow. Okay, 不可压缩、非粘滞流、稳态流. They are the quite priori knowledges and background for the Bernoulli equations. So that's another example. We have the straight line, like the dashed line showing here, and then we pick up the 2 points, the P1, point 1, and the point 2. And the question is, can you find the velocity in here, the velocity at the port of the tank? And you actually know the depth of the tank liquid is the 10 meters. So can you just predict the velocity at the port locations? So again, we apply the Bernoulli equation. So I quickly write down the Bernoulli equation. We have the P1. P1 is the point located at the liquid surface, and plus the gamma V1, and plus the 2 over rho V1 squared will equal to the P2 plus the gamma V2, and plus the 2 over rho V2 squared. So in the following exercise, we only write down the Bernoulli equations, and we see what happened for the items we need to take into account. So the first, I will say the condition 1, the P1 will equal to the P2 and equal to the 0 gauge pressure. The reason why you can see the P1, the 1 point here and the 2 are exposed on atmosphere environment. So there is no gauge pressures. OK? 就只要你看到那个计算的位置是暴露在大气里面的，那我们就不会有 gauge pressure. OK? So we don't have the gauge pressures, and we can rewrite if we don't have the gauge pressure, so we can rewrite, I just merge the D1 minus the D2, multiply the gamma together, and the right hand side I merge the velocity items, so we have the V2 square minus the V1 square. Okay, so our purpose is to compute how large the V2 velocity. Okay, so and then we can rewrite the equation, so we know that the V2 square minus the V1 square will equal to the 2 times gamma over rho and then multiply the elevation difference. And then we know that the gamma is a low g. So here we only have a 2g and D1 minus the D2. Okay, but in these questions, we don't know how the V1 velocity, and we don't know the relationship between the V1 and the V2. So how can we find out the V2 velocity in our questions? So the second assumptions, we assume the V2 velocity is quite much higher than the V1. That's because there is a different cross-section area. This cross-section area is quite wider, and this cross, the pole is quite smaller. So the cross-section length is totally different and comparable. So I can say that the V2 is always much larger than the V1. So I neglect the item of the V1. So I rewrite the equation. I only conserve the V2 square will equal to the 2g and the D1 minus the D2. That result, we have the root. The V2 velocity is equal to the root of the 2g and D1 minus the D2. So I put all of the number inside the equations. We have 2 times and 9.81 meters second square, and the 10 meter difference for the elevations. So you can use your calculator to confirm the answers. Okay, for me, I take a quick calculators, and the answer shown in my calculator is 14. That's the meter per second. Okay, so that idea is very simple. We just repeatedly write down the Bernoulli equations, and we see what happened and what items we have. If some items we don't have the information, so that means we should neglect the items we don't have. And then we can find out how velocity fast in our problems. Okay, so the second exercise is very, very famous in our design, the helmet. Okay, so this is a problem we design a helmet. So what's the problem when we design a helmet? So the problem is the ventilation. Ventilation is 通风的效果. So if you choose the different helmet, and you will consider which one is the better for ventilation. And how can we say that the ventilation is good? That depends on if there is a large pressure difference around the helmet. That indicates the flow the air can flow very rapidly. Okay, so that the ideas, I write down the purpose for the how can we quantify the ventilation problem. And you can see we have the pressure PA, the point in here, and we have a pressure PB. If PA minus the PB, we call that is the delta P. So the idea is if the delta P is large, and then we call that the ventilation of the helmet is good enough. If the delta P is not large enough, and we will say the helmet is not good for us. Okay, so it depends on the price. If you can see the helmet, there are some descriptions, and you can double check the ventilation abilities for your helmet. Okay, so that's the key knowledge. We should figure out how large the pressure difference. And if you see the right hand side, we have a different straight line. The first straight line is along the 1 to 2 point. And sometimes the point 2, we call that the stagnation point, right? And stagnation point, usually we know that the velocity of the V2 is equal to 0. That's why we call that the stagnation point. And the second, we have the additional straight line is on the top. It's like the red line here. And this is a straight line we consider from the point 3 to the point 4. So what the pressure difference we want? We should compute the pressure in here is the P2, because the P2 is like the PA shown on the left hand side. And we should compute the P4, because the P4 is equal to the PB shown on the left hand side. So for our questions, what the pressure I need to compute is I need to compute the delta P will equal to the P2 minus the P4. And I'm wondering to see how large difference we have in our exercise. Okay, so that we have the two different Bernoulli equations because we have the two straight lines. As I emphasize, if you want to apply Bernoulli equation, you should make sure the 2 points you pick up, they located at the same straight line. If not, you cannot apply the Bernoulli equation. So in here, we have the two Bernoulli equation, right? The first Bernoulli equations, we are focused on the point 1 move to the point 2. Okay? Because this is along the same straight line. So again, you can write down the Bernoulli equation very quickly. The P1 gamma Z1 plus the 2 over rho V1 squared will equal to the P2 plus the gamma Z2 plus the 2 over rho V2 squared. Okay, and right now you can consider the items you want and you have. So the first one, we consider the condition A, the P1 will equal to 0 gauge pressure. Because the P1 are located at the atmosphere, so there is no gauge pressures. And the condition 2, we know that the elevation at the point 1 to the point 2, they are the same elevation, right? So because they are located at the same elevation, so we can cancel out the items contribute from the D1, D2. Okay, so that I can cancel out some items, this one and this one and this one. And our purpose is we are trying to compute the P2. So we wondering have the P2, and the P2 will equal to the 2 over rho and the V1 squared minus the V2 squared, right? So we go back to see the questions. How can we know the V1 velocity? We actually know because the number is showing here. And how can we know the V2's velocity? As I mentioned, the V2 is a stagnation point, right? So we have the condition C. We know that we don't have the V2 velocity because the point here is a stagnation point. So we don't have the item for the V2. So finally, what we have? We only have the P2 will equal to 2 over rho and the V1 squared. And how can we have a density? Because this is the air, so we know that the density is 1.2 kilogram per meter cubic. Okay, so we directly simply just put the answer inside. And so this is 1/2 and the density 1.2 kilogram per cubic meter, and the V1 velocity is the 12 square and the meters and the second square. Okay, so you can compute the answer for the 1.2 divided 2 multiplied 144. So that answer is equal to the 86.4, and this is the part. As you can see the answers here, the pressure is quite smaller compared to 1 atm. Okay, that is only a little bit pressure caused by the flow air. Okay, so we know that the P2 pressure equal to these values. So we have the second questions is we wondering to answer how large the P4 pressure. So we change the different straight line. We change the straight line to the 3 point, go to the 4 point. Okay, so and then in that time we also quickly write down the P3 plus the gamma Z3 and this is Z3 and plus the 2 over log V3 square and will equal to a P4 and the gamma Z4 and plus the 2 over log V4 square. Okay, so again, and we know that what the item we can cancel out. The first one, also the P3, because it is exposed on the atmosphere, so we no gauge pressure in there. Okay, so and then our target is the P4 value. So we just keep the P4 is our target, and then move all the parameters together. So we have the gamma and D3 minus D4. And the second item is 2 over rho and V3 square minus the V4 square. And you can double check the V3 velocity we have in here, and we have a V4 velocities. But only one parameter we didn't know is elevation changes with the Z3 to the Z4. But as we know, the elevation changes in there for the helmet should be a view maybe centimeters, right? Should be a few centimeters. And as we also know, the density of the air is 1.2 kilogram per meter cubic. So the contributions from the helmet elevation difference caused by the pressure changes is quite smaller. It's quite smaller. Because the helmet, the height difference is only a few centimeters. So for these questions, I don't know how the elevation changes between the helmet, the middle point and the top. So I cannot figure out this item. And because of this item, the contribution is quite smaller. So we can neglect the effect for the elevation changes. So finally, we only know the P4 will equal to the 2 over rho and the V3 square minus the V4 square. And I put the answer in the number inside, the 1.2 kilogram per meter cubic. And the inside is the 12 square and minus the 18 square. And units is meter second square, meter square and second square. And so you can use the calculator to check the answer. Okay, I check by my side. And okay, the answer, I typed wrong. 144 minus the 18 multiply 18 and multiply 1.2 divided the 2. Okay, so the answer is the minus the 108 par. So you may curious about there is the minus. Don't worry, sometimes there will have the negative pressure, okay, at the different locations. So this is our second pressure's answers, okay. So we can compute the different pressures delta P based on the P2 and the P4, and you will see how large the difference they are. Okay, so sometimes when we design the different helmet, and we will have a different velocity on the top and a different velocity on the free airstream, and you will compute how large the pressure difference you have. Okay, so that's a very famous exercise when we design the helmet, and we just consider how large pressure difference on the middle and the top of the helmet, and we can we have a different quality of the helmet, and we'll have a different price. Okay, so that's the idea for the Bernoulli equation we apply to consider the ventilation of the helmet problem. Okay, so in the following slide, we are trying to move back, and I wondering to introduce the different device. How can we measure the velocity we want? Okay, and one famous, we call that the stagnation tube. Why we call that the stagnation tube? Because we put the L shape inside the flow field, and we will have some points. The famous point in here is our stagnation point, and we're wondering to measure the flow velocity in the free stream field. So we're wondering to know how large the V0 in there, and we actually know the V1 is the stagnation point, so this is V1 will equal to 0. But as you remember, we also introduced one methodology to compute the velocity. We call that the static. We have the static tube, right? In here, we have a static tube. So how different? You can see the static tube. We don't need to put the pipe inside the flow. We don't put the pipe inside the flow field. So our tube cannot disturb the flow conditions. But if we go back to see the stagnation tube, we need to put the tube inside the flow field. So this device will disturb the flow conditions. But it can easy to measure the velocity flow we want. Okay, so how can we measure the velocity? So for me, I reconsider again, we have the Bernoulli equations. So we consider 2 points, the 1.0 here, another point is the 1 here. And as we know, the 1 point here is our stagnation point, and V1 will equal to 0. And there are some diffraction height. We have the L diffraction height, and we have the D diffraction height, the water depth we want. Okay, so because we only have a diffraction height, so right now the Bernoulli equation, I use the headphone. So I use the headphone Bernoulli equations. So I know that the P and maybe the P gamma and plus the Z, and we have the P0 and the Z0, and 2G over VD squared over 2G, and will equal to the P1 and the gamma plus the Z1, right? And also the V1 squared over 2G. Okay, so initially we certainly know the elevations for the D0 and the Z1 are the same. So we can very quickly to cancel out the same elevation, so we don't need the D0 and the Z1. And then we know that the V1 is the stagnation point. So we don't have the item for the V1 square. So our purpose is how large the V0 in the flow field. So it's our purpose. So I keep the V0 square and the 2G in here, and I move the gamma on the right hand side. So this is the P1 minus the P0. And the V0 square will equal to the 2, and the gamma is a low G, so the button here we only have the low and the P1, and it's a gamma low G. Okay, so it's a P1 minus the P0. Okay, so that's you can see based on this equation, we need to know what the P1 and the P0 value, right? So for the P0, if you have the P0, and then you can understand what the pressure in here, because you know that the depth of a liquid is equal to the D, right? So we know that the P0 is equal to gamma D, okay? So what's the P1 pressure? Because the P1 is connected into the tube, so the total length for the P1 is the gamma, the pressure is equal to the L plus the D, right? So in equation here, you know that the V0 square and the 2 over rho, and you have the P1 is the gamma L plus the gamma D is the P1, and minus the P0. So the gamma D will cancel out. So inside you only have 2 over rho and the gamma L. And finally you have the 2GL. So you actually know the V0 will equal to the root of the 2GL. Okay. So after you derive the final equation here, so in the future, you only need to identify how large the diffraction height L here. And you can put this L into this equation, and you can quickly to determine how the velocity in the flow field. Okay, how the velocity in the flow field. So the stagnation tube is very convenient. We just put inside the flow field, and we observe how the L in here we have, and we put into the root 2GL equations, and we can rapidly to understand how the velocity in the flow field. Okay, and the second exercise, second device are very famous, and we call that is the pitot tube, 皮托管. Sometimes we call that the 皮托管. And if you see the pitot tube and how the tube we have, so we distinguish into we have the inner pipe, and we have the outer type, the pipe. And the two pipe you are familiar, because the inner pipe is here. I use the red color, yellow color in here, and we call that is the stagnation tube, 自流管. Okay, the inner is the stagnation tube, and as you can see the outside, so we have the outside tube, and like the blue color here, and we call that the static tube. So the pitot tube is combined two tubes together. One is the stagnation tube inner, and the outer is the static tube. So how the advantage, as you can see, I write down in here, the major advantage for the pitot tube that can be operated under the compressed conditions. That's we wondering to measure the velocity under some conditions under the compressions. And if we use the pitot tube, that can be work, but the other tube cannot work under the compression conditions. So how can we, based on the pitot tube, to compute how large the velocity in the flow? Okay, so the slide I put here, we are trying to derive the equation. As you can see, the final equation showing here, we have the pressure difference first, and then we can estimate how the velocity flow. Okay, so the main idea is how can we measure the pressure difference based on the pitot tube. So the idea, we go back to see the cartoon figure in here, wondering to consider the Bernoulli equation along the straight line like the yellow line showing here. So we make some balance for the Bernoulli equations. And here, the point here, again, because it is the stagnation tube, so the point for the one, this is a stagnation point, right? So the V1 will equal to 0. And outside the P point, the point here, the V2, that is the same velocity with the free stream velocity in there. So the V2 is the velocity we want to measure, to determine. Okay, so we along the same straight line, so we based on the Bernoulli equations, the P1 plus the gamma Z1 plus the 2 over rho V1 squared will equal to the P2 plus the gamma Z2 and plus the 2 over rho V2 squared. Okay, and one thing we know that we can neglect because the V1 is the stagnation point, so we don't have a V1 velocity. Okay, so that means we can rewrite the equations, and there is I use the piezometric pressure 1, and there is the piezometric pressure 2. And I know that I rewrite the equation where 2 over rho V2 squared will equal to the piezometric 1 pressure minus the piezometric pressure 2. And we call that is the piezometric difference is a delta P. Okay, so you can understand why the V2 will equal to the root of the 2 times delta P divided the rho. Okay, so the pitot tube, the idea is we have the delta P measured directly from the pitot tube, and we put the equation here, and we know that the fluid density, so we can compute the velocity very quickly. Okay, so that the ideas for the Bernoulli equation applications, one of the famous applications is trying to put some device and measure the velocity in the flow field. So how many tubes we have? We have the static tube and the stagnation tube, and finally is the pitot tube. Okay, and the pitot tube is combined the stagnation tube inside, and the outside is the static tube. Okay, so that's a very basic idea when we apply the Bernoulli equations. We can write down some important phenomena to describe the velocity it is. Okay, so I think we can finish the exercise here, and then we break 10 minutes. Okay, so let's say we have the pitot tube inside here. So we put the pitot tube, and we connect the pitot tube with the manometer. So the yellow device here is our manometer. As you remember, the manometer is trying to measure the hydrostatic pressure difference between two different points. Okay, so if you remember, the question is we wondering to compute the velocity downward of the kerosene. So our target is the kerosene. So we wondering to compute how fast the velocity in here. So we wondering to answer this question. So the first we should based on the equation, because we put the p-tode tube. So we know that the velocity should be equal to, based on the equation we derived in the previous slide, is 2 times delta p and divided the rho, right? So the major idea is how can we know the delta p? So we put the manometer here, and we have the point 1. So this is the P1, and here is the P2, right? And we connect the manometer. So we know that the delta P1 based on the, so right now we are based on the hydrostatic equation. If we still remember the hydrostatic equations, the P1, and we will downward the D1 to the minus the D2 elevation difference. So we should, the pressure start from the P1, we should plus the gamma kerosene will multiply the D1 minus the D2 elevation difference. How I use the plus? Because the point start from here, and we are going to the down, and going down, and the pressure increase, right? So that's why I use the plus. And the material is the kerosene. Okay, so I use the gamma K indicate the kerosene specific gravity weight. And then I also going down with the L length, and also with the kerosene material. So I also going down, so I use the plus the gamma kerosene, and right now is the L, right? So the gamma K multiply the L. And then right now I'm located the point here, and I'm wondering to go back to point here. So I need to going up, right? But right now when I going up, the material I change to be the mercury. So the material I change to the mercury, and this is the going up. So I need to minus, and the gamma N is our mercury specific weight, and we have a diffraction is the Y, okay? And then finally, I wondering to go back from this point to here, and we need to consider the distance difference in here is the L minus the Y, okay? And this is still going up, so the pressure is decreased. So, and the material I change it to the kerosene. So this is the gamma K, and the length is L minus the Y. And finally, I can go back to the P2, right? Finally, I can go back to the P2. So I expand all the parameter we have. So the P1 plus the gamma K Z1, and minus the gamma K D2, and plus the gamma K L minus the gamma M Y minus the gamma K L plus the gamma K Y. Sorry, there's the K, the gamma K, and there's Y, and equal to the P2, right? And we know that the delta P here is the piezometric pressure difference. So I merge some items. This is the P1 plus the gamma K Z1 is the piezometric pressures for the point 1, right? Because it's the P and the plus the gamma Z1. So similar, I change I move the P2 to the left hand side. So there is the minus, and this is the P, 2 plus the gamma k d2. This is the items for the piezometric head of the point 2. So the two items minus together is all equal to our delta p. And what will equal to, the delta p will equal to what? So the first I double check the item. I already used the items for the 4 parameters listed in the equations. And you can also cancel out the gamma L, gamma KL, and the minus gamma KL here. So we only have the right hand side is equal to the two items. The two items is this one and this one. So I move to the right hand side. So that will equal to the y. I keep the same parameter outside. And the inside is equal to the gamma n minus the gamma k, right? Okay, so we certainly know what's the delta p. The delta p will equal to the y and the gamma n minus the gamma k. And we know that we don't have the gamma n, the gamma k, but I have the specific gravity in here. So I replace the gamma n by the gamma w multiply sg n minus the gamma w multiply sg kerosene. I use the sgk. So I can take the gamma w outside. So the outside equal to the y gamma w. And the inside is sgn minus sgk. Okay, so I have the delta p. And then what is our velocity? So I apply the equation shown here. So the v will equal to the root. And the delta p I write down here is y gamma w and sg n minus sgk. And what the density I need to divide it is the fluid density. So the bottom row here is the kerosene. It's the kerosene density, right? And we know that the kerosene density, we don't have the kerosene density. So the gamma W I rewrite to the rho WG. And let's say SGN minus SGK. And we don't have a rho K, so I will use the rho W multiply SGK, right? We don't have the rho K, but I know that the rho K is equal to the rho W and the SGK. And so I can cancel out all the same parameter, the rho W. So finally, I can say that the velocity inside the tank, the kerosene velocity will equal to the root, the y, g, and we have the sg m minus sgk divided the sgk. So we can put all the parameters inside the equations. And maybe you already forgot the 1g is equal to, the gravity is equal to the 32.2. Okay, the ft second square. That's why, because we need to use the imperial unit, because you see the final answer is equal to the ft divided the seconds. Okay, so we put all the parameter we have. So the y diffraction height in here, the diffraction height in here, we know that is a 7 inch. So the y is equal to the 7 inch, and we convert the 7 inch divided the 12 to be the ft. Okay, so you know that the inside, the y here is 7 divided the 12 Ft multiplied 32.2 Ft second square, and the SGM is the 13.55 minus the SGK kerosene is 0.81, and finally divided the 0.81. Okay, so you can double check the final answer should be equal to the 24.3 Ft per second. I don't have the time to check in my site, but you can put all the number inside the equation and use your calculator to double check the answers. Okay, so that's a very good exercise. We cannot forget everything we learned before. Because for this exercise, we need to understand hydrostatic equations. And then we know that how can we compute the delta P. And based on the Bernoulli equation, we know that the velocity is equal to root of 2 times delta P divided the density. And so we put the delta P inside the equations. And based on equation, we can rapidly estimate the flow velocity in the field. Okay, so that's a very nice exercise. I'm wondering to finish before we break. Okay, so I guess we have a 10-minute break and we go back to finish the class. And we will have the quiz, okay?